This is my group. Most of them are still with me, but this photograph is from Indiana University. We really haven't gotten time to take a photograph in Dallas. So before I start, it's always a thanks to the key players, my students. Tushar, Philip, and Shuo have graduated. The ones in red are still my PhD students. The green one is a master's student whom I'm trying to convince to a PhD. So I wasn't sure if this should be green or not, but because he's seeming to lean towards doing a PhD, I thought I'll go with the green color. Thanks to my collaborators and funding agencies as well. So I know and I realize that it's a 4 o'clock talk. So if you're going to take a nap, feel free to do so. But after this one slide, so what I'm really interested in talking about today is this notion of human-allied artificial intelligence. As Prasad mentioned, I'm going to talk about learning and reasoning in structured noisy domains or statistical relational learning, but bringing human in the loop of statistical relational learning. So how can I use a human expert to learn better and kind of seamlessly interact with humans while I'm learning my models, okay? And we also do some work in the sequential decision making side, particularly on this problem of inverse reinforcement learning. So everywhere I'm going to flash a slide and I'm going to say this is an aside because we can do the same thing for sequential decision making. But the key focus will be on statistical relational learning, and I explain what that means. The adaptations of our algorithm are mainly designed towards precision health tasks. So we are looking at electronic health records, we look at clinical study data, we look at clinical images, and now we have recently started working with survey data, predicting postpartum depression, predicting rare diseases by looking at how people answer to surveys. So we have a bunch of data sets that we are working on from a health perspective, and we are interested in applying and adapting these algorithms for health tasks. So I'm going to mention the health tasks as and when they are relevant. So the key question is what is the big goal here? The big goal for us is humans somehow can have the ability to get so much done from so little knowledge or so little data. And to do that in a real machine, my hypothesis at least, is let's make the domain experts more effective. In the sense that, for instance, tomorrow I'm talking to a bunch of clinicians who work in neuroradiology. How can I tap the expertise of a neuroradiologist to give me the most relevant information when learning a classifier? Or how can I tap his or her expertise in developing a good treatment plan for somebody that I know has Alzheimer's? Okay? So, and to do that, the idea is also to kind of calm people down about this public perception of AI and say, actually, many of us can use these machines on a daily basis, and actually it's going to make our life better. I'm hoping so. And of course, make the machines think, and I'll get to that. This is kind of one of the meat of our problem. Can a machine know what it knows and solicit information about what it does not know? Okay, so those are the three questions, and I think that what I'm really interested is at a big picture level, somehow can I leverage the human expert, the domain expert's knowledge for reducing the cost of learning. So this is why I'm calling this as human allied AI. The human and machine are really allies, and it kind of fits nicely when you talk to clinicians, because you kind of reassure them of the fact that they are really allies and not enemies. But I also like it only for the fact that it nicely rhymes with high. And because each AAI becomes high, and that's nice. So the idea here is, can we build systems that can seamlessly interact with, learn, and collaborate with a human expert? Okay, and I'm hoping that I'll convince you that we are taking the first step in this direction. But when I think of this human allied framework, there are several smaller instances of problems that we have looked at, that we as us and the broader community have looked at, that falls under this realm. And one of them is actually my PhD dissertation, where we were looking at this notion of assistantship learning. Prasad, Alan, myself, and another graduate student, Judah, we were working on a bunch of algorithms on this side. And so think of a decision support system, a clinical decision support system that's residing inside a EHR. And I can learn basically using any kind of data, electronic health records, some sensor data, wearable data that I have, some genetic sequence that we already have been doing over patients. Now you can build a graphical model or set of graphical models for disease state phenotype prediction, use that into your planning framework to develop treatment plans. So now a new patient walks in, the physician puts all the parameters of this patient and then says, ooh, Sriraam, you got to take this medicine. And then the system should probably prompt that person and say, wait, he's already on Prilosec. Now if you give him Pravix, there is proof that it causes stroke. Okay? I didn't make up this example, it's actually true. You can't take Plavix and Prilosec together. So now that's something that some clinicians may know, some may not always keep in with the literature, current literature. They can't keep abreast with the current literature. So how can we bring this knowledge to the clinician? A better example is actually when I was meeting the doctor 3 months back, and when I always go to the doctor, I have my phone like this because that conversation is not always great. So I'm doing this, and the doctor asks me, okay, are we done? Have you told me everything that I should know? My answer is yes. And then my wife whacks me on the back, and she says, you forgot the most important thing, you have diabetes. I'm like, oh yeah, sorry, I forgot to tell you. But it's not because I didn't want to tell him. It's not a taboo. I'm telling you guys, so I don't mind telling him. But the fact is, at that point, I was distracted, so I didn't care to tell him. But the machine knows, and the machine can prompt. So how can we build these systems that can actually help the physician come up with better decisions, and how can we roll it over, right? I mean, it's a simplistic scenario that I keep talking about, but you can think of more complex scenarios. So this is an instance of human-allied AI as I see. The other one that we classically work on is this apprenticeship learning, where the assistant kind of learns from the human to probably do some subtasks that the human can do by himself or herself. And so how can I basically relegate some part of my work to the assistant so that the assistant can do it faster than maybe I do, right? Maybe segmenting an MRI image and teasing out the most important regions of the brain that I should do when I'm looking at an Alzheimer's. How can I automate it? Right, that's kind of again a human-allied AI problem, or the recent problem that we have been working with in DARPA called communicating with computers, where, as the program manager Paul Cohen nicely put it, you have a machine and a human who are collaboratively trying to learn together. So he says you can think of them as two children, and they say, "Ooh, I have a horsey, you have a horsey. Let's go figure out how to play in the park together." So this is this idea of communicating with computers, because you have to figure out what kind of vocabulary can they communicate, right? And I could say put that block in an L shape, and L shape can be in multiple forms. Now the machine has to figure out what I mean by an L shape and ask me which type of L am I talking about, and get that feedback. And over time, the hope is that you talk like you talk to a friend. Over time, you understand each other so much that you don't need to learn more, and the communication actually reduces over time. That's the idea, right? So this again, I see this as another human-allied AI formulation. So that's why I think the set of problems that we work under can broadly fall under this idea of human-allied artificial intelligence. And I'm going to focus on some of these and talk about them in more detail. But before that, when I think of, well, what are the requirements of human-allied AI? These are some requirements that I think are important. Things like multimodal data that we have to handle. We have to reason with very large domains. Particularly in electronic health records, we have these various domains that come, various data sets that we have to somehow merge, match, and then learn from it. I also think that faithful temporal modeling is necessary. Simple dynamic Bayesian networks and hidden Markov models do not always work. So we need something that's even more faithful. Like when I'm predicting when somebody is going to have a heart attack, I can't just say, ooh, it is going to be in the next 6 months, and that's not really what you want. You want something that's much closer in time, and I'll talk about it. Of course, effective sequential decision making. Oregon State is a leader in this area. Scalable learning with complex relational data, which is what I'm going to talk about today. An explicit modeling of noise and uncertainty. So these 5 and 6 are where I'm going to focus, but I'm just going to touch upon the other things that we have been doing so far. For multivariate data, we have been recently interested in count data. So we started looking at basically things like word counts in documents, cell counts, the number of times somebody is going to be readmitted in a hospital. We just got our paper accepted on predicting the number of times a procedure is going to be done on a patient, because that's important for hospital resource allocation. And so to do this, what we have done is we have started looking at some Poisson graphical models, and again, what we have done is we have developed this notion of Poisson sum product networks. This joint work with Christian Kirsting and his students, where you can look at these Poisson sum product networks as really a way of testing independence of Poisson random variables. So you can actually figure out if two Poisson random variables are conditionally independent using our sum product network. I'm going to skip all the details, but really what we are doing is we are learning a bunch of Poisson dependency networks. Dependency networks are cyclic Bayesian networks which approximate the true joint distribution. So our work is kind of an approximation of a Poisson dependency network. And again, we have extended this to handle multiple distributions, where the other types of distributions are also used for in the Poisson sum product networks, and it's under review. So this is one direction. We've been working, as I'll explain again, we'll be working on other types of distribution and not just multinomial. We have been working on this problem of lifted inference for quite a while, which is this idea of taking a large graph that you're interested in querying, and maybe compressing it into a smaller graph somehow, and such that this compression would still make it not too much of an approximation. And how can you obtain such a compression? And maybe you take your original algorithm, maybe loopy belief propagation, and you can actually run some form of a modified loopy belief propagation that is guaranteed to yield the same result as your original graph. And so in some cases, for instance, we have achieved like 100 times speed up, and it's working pretty well. So this is the idea of efficient reasoning or lifted inference that we have been working on. The third direction that I think we are making some headway, and I'm kind of pretty pumped up about it, is this idea of continuous time. As I said, if you look at a discrete time model like a hidden Markov model or a dynamic Bayesian network, you have to discretize time. You have to talk in terms of days, you have to talk in terms of hours, you have to talk in terms of years or whatever. And if you can have one of two problems, you might either discretize it too much, in which case you will not have observations for a lot of time points, or you might discretize it too coarsely, in which you are missing a lot of events in between. So on the other hand, there are these idea called continuous time Bayesian networks, which view time as a continuum. Really, it's just very simplistically, it's just putting like an exponential distribution over time. So the longer you wait, higher is the probability of something happening. Okay? Easiest example is the longer you wait, the higher is the probability of you dying. Right? All of us, it's true. We're going to die at some point, and the longer we wait, higher is the chance that we're going to die. So you're going to take that and kind of compute, again, I'm simplistically talking here, compute an expectation over the distribution that could give the expected time of an occurrence of an event. And that seems to be working well for us in many of these clinical problems. We are also interested in sequential decision making. Again, I'm not going to do too much in detail, but things like teaching a system, let's say how to drive. This is a classic example, because advice is something that everyone gives for free, right? I mean, nobody is accountable. Everybody gives you an advice. And when you are the first time driver, you're sitting in a car, people sitting all around you, they give you 1,000 things, right? They won't do it, but they'll tell you, ooh, you're driving too fast, you're changing 2 lanes too fast, this. The question is, as a learning system, how can you figure out which of these are important? Which of these should I take, and which of these should I ignore, right? So we are investigating into issues on this, on imitation learning, inverse reinforcement learning, planning, and POM-DP. So these are kind of the higher level things that we are doing. So what I'm going to do is talk about what we are doing specifically. As I said, we are learning these relational probabilistic models, and we are applying it on electronic health records, on clinical study data, and so on. But I'll talk about these when we get to it. Okay. So if you think about it, how many of these machine learning practitioners, many of the time the industry thinks of what we do is that we have the data in a spreadsheet, and we just apply data mining on top of it. Pick your favorite algorithm, whatever that is, and maybe you apply deep learning today, deeper learning tomorrow, deepest learning the day after, and it somehow works magically, right? So that's what we think about all the time. But the problem is that many real data is not so simplistic that you can fit it inside a nice feature vector. And so the heterogeneous networks are a lot. We like this example of visual genome. That's a classic example where the data seems to be much more relational. The data is in a relational database, and we want to learn with a relational database. As another classic example that we work with is an electronic health record. And you look at this electronic health record, it has a lot of noise, it has a lot of uncertainty, and you got to reason with this, but most importantly it's structural. So it's not like this lab visit is independent of this lab visit. They are probably the same lab test as part of a single disease diagnosis. Similarly, you can't say patient 1 is independent of, I don't know, doctor 1. The doctor 1 is actually the one who is teaching patient 1. So this, you can't apply these independencies easily. You can't unroll many of these data into a nice flat feature vector. So what you want are learning algorithms that can learn at the level of the structured data, and they should be able to handle noise and uncertainty, right? So there's again dependency that exists between objects, there's noise and uncertainty that can exist, and so what we are really interested in is, can we somehow learn from these data that are in these databases. So really, if you think about the modern data science, what is happening is we are all trying to deeply understand the data. So all of us dive deep, and there is this data set that many of us are going to bang against it, so we'll do whatever we take to construct these features. And the problem for us is that the real data comes in large number of formats. There could be multiple views of the same problem, or they are actually related views that you have to somehow superimpose to get the one coherent picture of this problem. So if I think about the methods that I need to put together, they are everywhere. You need things that model uncertainty, noise, we need methods that scale well, we need representations that can represent this complex structured data, and we need learning methods that come from, I don't know, data mining and machine learning community. So we need to put all of these together to get a final a good model, right? So when I think of it, you can think of many methods in which these things have been done, right? So if you just look at learning, it's been there for a long time. Logic, again, a long time, which can represent the data. Probabilities can represent noise and uncertainty, and we've been researching into that for a long time. And we started putting things together. Logic and learning, there's this field of inductive logic programming, learning and probability, active learning, expectation maximization. You can do all kinds of learning using probabilistic methods. Logic and probability, again, there's been some work from 1985 by the seminal paper by Nils Nilsson. There's a lot of work on probabilistic logic and stuff. And that brings me to the area that we work on, which is this idea of statistical relational learning, where we have a higher order representation. So we can represent the data in first order logic format. You have learning on top of it, and stochastic model in the sense that we can model noise and uncertainty very well. At this point, I really have to quote Alan Fern. The first time I showed him the cube, he says, everybody likes to put their cube on their star on the top, right? So if you're a grad student, take this with a pinch of salt. He's perfectly right. So whoever is presenting is always going to put their star at the top right corner, because that's where it's like the Christmas tree. That's where you need your star. So from my side, I think it's justified because we have structured data, we can do learning, and we can handle noise and uncertainty. Okay, but again, when somebody presents a cube, think about it. Why it is presented this way? So I know I've been trying to talk abstractly, so I'm going to try and concretely talk about a single example of why this is a little bit more relational than standard feature vector. So for instance, this is a simple tree called as a relational probability tree, and here I'm looking at let's say predicting if a person is going to have heart attack. So then I'm going to look at if the person is male, and it's very well known that men are more prone to heart attack than women, but of course heart attack is much more lethal in women than men. I know somebody who was a male who survived 7 heart attacks. It's very hard for a woman to survive 7 heart attacks. So that much is well known. And now if the person is a male, then you look at the cholesterol level of this person at over age 40 is over 200, right? So if the cholesterol level of this person above the age of 40 has ever been over 200, again this is a made up tree. So you think of this person as a timeline, you chop the line at 40 and you see, is there ever a cholesterol level that's greater than 200? Then the probability of getting a heart attack is 0.8. If you are over 40 and your cholesterol level is over 200, do not get a heart attack. This is a made up number, okay? And this is a made up tree. So what this shows you is I can actually search for this thing called existential. I can say, does there exist one measurement such that it's greater than 200? It's not this easy to do this in a propositional setting. I can also look at if the father of the person has diabetes. Okay, if this father of the person has diabetes, you can actually look at things like if there exists a friend who smokes or the number of friends who smoke. and so on and so forth. So you can make this as expressive as you want. And then you can start looking at the BMI of the person at the age of 55. What was it? Okay? So what I'm trying to say is you can talk in terms of objects, you can talk in terms of relationship between objects, you can talk in terms of specific values of these attributes and objects. And that's the power of first order logic. You get that. So what our learning methods do is kind of learn these trees from data. From relational databases, I can learn these trees to learn these trees. So what I'm going to talk next is how do we learn these trees? How can I interact with a human expert as advice? And finally, how can I seek advice in a seamless fashion? By the way, I'm going to stop for a second if anybody has any questions so far. Okay, so what I'm going to do is now talk about how I can learn these. This is kind of an older work because it's now about 6-7 years since we have done it, so I'm going to rush through this very quickly. But what we do is we build upon this machinery of functional gradient boosting. Now many of you, the young students, know it as XGBoost. And so what we are really doing is taking XGBoost and do it in with structured data. Okay? So the idea is very simple. You have a current model. You make predictions based on the current model. You have your data. You compute the difference between data and the predictions. That becomes what are called residues or gradients. You fit a regression model to that residue and keep adding the model until the final model is simply a sum of these regression trees. And why it works is pretty simple. I'm going to skip the details, but yeah, the idea is that you go from a parametric representation to a functional representation of the conditional distribution, and now you take the gradients with respect to that functional representation. And what happens is that instead of now computing the gradients over all the examples, you can compute the gradients for each example separately. Okay? And you can fit a regression function that fits all the examples, the gradients of all the examples. Now what happens is the regression function that you fit is going to point in the same direction as your original gradient. They may not be the same in terms of the number, but the direction is generally going to be the same. So this is all proved by Jerome Friedman. The thing that we do is the gradient, the regression function that we fit is a relational regression tree, the one that you saw earlier, but instead of probabilities on the leaf, we have regression numbers between, I think, -10 and +10. And so the key is obtaining the gradients. The gradients are generally between -1 and 1 because I is the probability of it's I of x equals true means is this data true in the data set minus the probability of it being true. So you're asking, so let's say I'm predicting probabilities and Sriraam has a heart attack in the data set, and and my model predicts that I'm going to have a heart attack with 0.65. Then my gradient is going to be 1 minus 0.65, that's 0.35. Raviv looks pretty fit, so he's not having a heart attack, but the model says he has a heart attack with 0.12 probability. He's going to be 0 minus 0.12, negative 0.12. So the idea is all positive examples will have a positive gradient that you push towards 1. All negative examples will have a negative gradient that you push towards 0. So looking just at this data, you can say, ooh, that one was a positive example. These two are negative examples. So subsequent iterations try to push positive examples towards 1 and negative examples towards 0. So that's really the idea here, and it actually works really well. We have applied it on a whole bunch of problems. As I said, we have learned these models called dependency networks, which are cyclic graphical models. We have learned the beast, the Markov logic network. It was structured learning of a Markov logic network was nearly impossible, but we have algorithms that do that efficiently. As I said, we can do continuous time models. Actually, this is the one case where we show that the objective function is concave. So actually our algorithm is guaranteed to converge by this boosting. That was pretty well received. This was IIII 2016. We've also learned with the hidden data. The problem with let's say a relational database in many cases, or most of these logic based approaches, is they apply what is called closed world assumption. What you observe is not true. Here on the other hand, we can actually show that with this boosting approach you can do like an EM type learning, and that learns pretty well. We've been working on real-time strategy games for some time. That works, and transfer learning and so on. Very recently, this is still under review, so if you're a reviewer, I'm sorry for saying this, we started learning relational reinforcement learning problems. So we are looking at these relational trees as a way of approximating the values of a relational policy. Okay, so again, I'm not going into the detail, but what we have done is we have compared against things like the deep network, which we have to, and least squares. This is really the difference between, wait, what am I plotting? I'm plotting the difference between learning a single tree, a deep network, or a least square with our method. Okay, so anything over 0 means our method is better. Turns out that our method is better in almost all the problems that we ran this on. I'm just presenting 2 examples, but so turns out that this can be learned. We can learn multiple types of distributions. Again, multimodal data is important when you start working in real data, particularly electronic health records. So we have ways we can learn multinomials, exponentials, and Poisson. We have started, we actually now have Gaussians, and we can learn that too, and it works great. Impressive results on standard domains, the typical statistical relational domains. The key thing I want to show is that compared to the state of the art, we have better performance, a huge improvement in performance, but an order of magnitude 36,000 times speed increase, because we are not learning a single model, we are learning a large set of small models, and that works great. But we've also extended this to several real applications, all the way from cardiovascular study, electronic health records, to handwriting recognition, actually on IBM data, to more recently, this is our biggest implementation till now. There is this company called Career Builder. We are trying to convince them to use our recommendation system. We have shown that our system can scale up to 10,000 jobs and 30,000 applications. So you can think of the cross product, right? For that number of people, we were able to scale. Of course, it took us 10 days to learn, but who cares? At the deployment stage, we can make this recommendation in a matter of seconds. So we can learn even for large-scale recommendation systems. So we were combining collaborative filtering with content-based filtering together to do this. This has just got accepted as a paper, and hopefully we'll do this. But you're welcome to try this. The entire code base is up online. We have, I think we have written a nice tutorial showing how to use it. The biggest problem is setting the background knowledge with these logic-based systems. So we will walk you through it. We just built a user interface where you can give me an ER diagram and help you go through and do this background knowledge specification. So this is out there. So in case any of you students want to try running this, feel free to email me. We'll be happy to help you run this. Any questions on this part before I move on? Okay, so in the next around 20 minutes, and I promise I'll stop in 20 minutes, I'm going to split in 2 directions. One is the idea of advice taking in these SRL models, and the idea of actively seeking advice. So what we have done so far is I've given you a method that can learn purely from data, okay, and it learns well, it works, scales, at least I'm advertising that way until you try. The next step is, what if the data is noisy, and why are we ignoring experts? So what can we take from the expert, use that to learn and make our models better? So can the expert provide more information than simply the data? Can they give us advice about the data? And I'll show you what those advice means. The third step is, well, this second step is still going to take all the advice in advance. How can the system ask questions and get advice? Okay, so that's the third one. So I'll come to that, but the claim for advice-based representation is that statistical relational learning, as I said, uses first-order logic as the underlying representation. And first-order logic was the representation that people used back in the day to design expert systems, right? So you were able to provide knowledge to these learning systems based on logic, and many of these knowledge-based systems used logic. But somehow, research inside SRL was only data-driven. We were not able to exploit the human knowledge. So the question that we were asking was, how can we exploit that knowledge? So on one side, you have the experts providing examples. So they are just mere labelers and nothing more. Okay, a human is a mere labeler providing labeled examples. On the other side is where the human is an all-knowing oracle who writes the entire system, and all we are doing is deploy the system, and at deployment time we just do reasoning. Okay, so what we want to do is go from this mere labeler to somewhere in the middle where we had these weight learning, like EM based systems, where if you're doing a Bayesian network or something, somebody gives you the structure of a Bayesian network and only you fit parameters, right? So that was easy. To this oracle, so the question we were asking is, can we do something in between this space? So what we are doing is this kind of idea of advice giving. Okay, you can also argue that active learning, feature selection are in this space, but I think I want to be closer to the center than here. Okay, active learning is still closer to here because the human is still only labeling examples or choosing features that your learning system should do. But I want to do something richer. Can I do some kind of advice? And so what do I mean by advice, right? The several advice that we consider, the one of them is this classic qualitative constraints, monotonicities and synergies. Tom Dietrich had a nice paper with his student Eric Altendorf back in 2005. And the idea of monotonicities are very simple. You can say things like, as the cholesterol level of a person increases, the risk of heart attack increases, or as the exercise of this person increases, the risk of heart attack decreases. Okay, so you can specify these statements. You can do synergy statements, which are even more richer. You can say things like, the probability of having a heart attack is higher if in persons who have high BMI and high blood sugar level than with people on low BMI and high blood sugar level. Okay, so now what it happens is it talks about the influence of two variables, BMI and blood sugar level, on a third variable, heart attack, but it doesn't quite tell you quantitatively what this interaction is. It kind of gives you a higher level picture. So it just tells you how a probability mass shifts instead of saying this is the exact correlation. Okay, so that's what monotonicities are. The cool thing is you might think that precision recall is not that important, but actually in many real domains it is. Okay, so very simply think of Ebola or something. I'm building a system that predicts Ebola. Okay, so what's the worst thing that's going to happen if you have a false, let's say, false positive? If you have a false positive, and positive means Ebola, okay, not in a social case, but in a machine learning sense, positive means somebody having Ebola. So if you have a false positive, you're going to quarantine this person for 4 more days. Okay, so clearly this person is going to go out and sue you. Okay, few $1 million. Okay, what if you have a false negative? You let a person out with Ebola, and then epidemic, right? That's $1 billion, not $1 million anymore. So if I have a knob, then you're going to say, ooh, I don't want any false negatives, but it's okay to have some false positives, right? Recommendation system is exactly the opposite. Even today morning, I got an email from LinkedIn that says postdoc position is available. Jobs that suit your profile, a postdoc position. I did my time. That was 8 years back. Now I don't want a postdoc again, right? But I keep getting this. If you think about job recommendations, you don't need all the job recommendations in the world. The ones that you get, it better be right, right? So that you want to maximize precision there, not recall so much. So the point is that we want to have systems that you can turn this knob and ask, ooh, can I somehow give you this feedback trade-off between precision and recall, and you can learn better models. Turns out that we can actually learn better models if you have good precision recalls. And of course, the last one that we are also thinking of is preferences. So things like, I should be able to ask the person, ooh, this is a stop sign, what should I do? I prefer you try and stop the car. Like I was in Bloomington for 4 years. Of course, the same thing in Corvallis. You're surrounded by students all the time. So if I'm sitting with a donut and a coffee on top of a building and I watch how people drive through stop signs, only 50% of them stop. 50% of them roll through and drive fast or something, right? So as from a learning system, there's a lot of noise. How can I avoid that? By asking advice. Advice is you can say, I prefer you stop because I don't know what the exact action is, but I prefer that you stop if it's safe to stop, right? And you want a system that can incorporate this. On an aside, we've also been working on this notion of privileged information, where some information is available during training, but not during testing. As a classic example of an MRI, I may have electronic health records and fMRI data that I get, the imaging data, but then there could be things like cognitive testing and clinical and variables that I put on people during a clinical study that may not be available when I'm deploying this system. Because when I'm deploying this system, all I'm going to do is sit with the physician and I'm getting only their electronic health record and their image. I have to make a decision based on these two. But the idea is knowing these during training can help me learn a better model for testing. So this is called privileged information. Vladimir Vapnik introduced this about 8-9 years back, and they were doing in the support vector machine world. Now we are doing in the boosting world, and we seem to be doing okay on this as well. So when I keep talking of advice, what do I mean by this advice, right? So you can say things like in images, for instance, you can say something like membranes have many neighbors. When my student Philip, he got a job at Los Alamos National Lab, he was very proud, right? He got an internship. He's like, I'm going to look at macroscopic NASA images, right? What he didn't know was they had a different plan for him. They gave him microscopic fruit fly images, and they wanted him to work with it. So initially he was disappointed, but quickly we realized that was actually a nice opportunity, because when you are doing these microscopic images, because they are so tiny, humans miss many membranes. Segmenting, right? During segmenting we miss a lot because they are so tiny. What they can do, of course, is tell you what not to do. Like, I can tell you that membranes have many neighbors. You can take that and then isolate a membrane very quickly during segmentation. Okay? Similarly, it's like this. You can slow down for red lights, right? He gives this nice example that whenever his dad used to teach him driving, he'll run through a stop sign, but he'll turn, or a red light, he'll turn around and he'll say, but you cannot do it, right? So the action is wrong, but the advice is right, right? You cannot do it. You cannot run through a stop sign. So those are classic examples. We were even doing this in transfer learning, where, for instance, your data might be driving, your source data might be driving on a straight road, but when I am applying it, I'm driving on some curvy landscapes. And now I can give you an extra piece of advice that says, here the roads were all straight, but here I prefer that you slow down when you're coming to curves. Okay? And the system can take it. It basically takes them also as some kind of trees and learn from it. So in the boosting model, you can simply think of saying, why not use this knowledge that I give you here as the first model, and you can use that to learn. Okay? So what I give you as advice, use it as the initial model, classify the data and learn from that. Okay? The problem with that approach is that if I use that as an initial model, then over time my boosting will fix my model, because it relies a lot on the data. Remember the I minus p term? That kind of overfits pretty quickly beyond certain time. So if you have noisy data, the advice is lost. So instead what we have done is we actually put the advice directly into into the learning objective function, and when computing the gradient, we compute both using the data and the advice. So what we have done is, instead of using only this the sigmoid function, we add a cost parameter, and the cost is simply the number of times you satisfy advice minus the number of times you violate an advice. So ignoring all the details, when you do the math, crunch out the math, it comes down to this nice combination of two things. The first thing is the data that you saw, I minus p. The second thing is the advice. So it's really a trade-off between how much you satisfy the data and how much you satisfy the advice. And of course it's a choice of lambda. And what we have done is empirically shown that as long as lambda is within a fixed range, reasonable range, something like 0.3 to 0.7, it works great. You don't want too much weight on the data or too much weight on the advice. So as long as it's within a reasonable range, it works great. Again, as an aside, I keep saying that we'll do this for sequential decision making. So you can do the same idea in linear program, and this was our ICDM 2013 paper, where we showed that you can do this in the case of inverse reinforcement learning, where you are observing a trajectory and inducing utilities from it, and same thing, same idea applies. You can constrain the data and advice. I'm going to skip this, but again, on these the fruit fly images, we actually achieved a 99.1% accuracy. That was pretty awesome, because without this they were at around 70% accuracy, because that if I just train based on the images that they segmented, it was not useful because the segments were very noisy. But the most important thing was the noise was always around certain regions, because that's like the systematic noise that people introduce when they do things repeatedly, and advice helps fixing that systematic noise, and we actually got to excellent results on this. Same thing with the knobs that I keep talking about, the precision recall. Again, in several domains we got great results. Again, the exact relation between precision and recall is not that important. Okay, you don't want to say precision is 10 times more important than recall. You can just qualitatively tell me something. Precision is far more important than recall. I can learn it. Okay, you don't need to exactly tune the parameters for these learning algorithms. The recent success for us was in the NLP thing that I talked to you about in the morning, where we were looking at some sentences and use them as advice. So we talked to some physicians and said, well, if you are looking at medical abstracts, how can you write knowledge? And they were giving us rules and I'm giving you the most important things. You asked me in the morning, were you looking at some specific words? We were looking at some specific phrases. Drug-induced effect, effect after drug. And you can give these as advice. And the learning model actually does much better in terms of like area under the recall curve than learning without advice. And we did pretty well on this as well. Any questions on advice giving before I talk about seeking? Yeah?
So you had a question before where you were comparing predictions and advice. Right. So if the prediction is moving left, and what would be the advice over there? Is it again an action?
So the advice could be over sets of actions. So I could say, you could say, I prefer you go north or west, but don't go south or east. Okay? So I want you to be in this general direction, don't go in this direction. But the data is going to be exact. It's going to tell you I went left or I went west, right? So advice could be just over sets of things, but it doesn't have to be over, it's not over one label. It could be over sets of labels. Does that make sense? Did I answer your question? Okay. All right, so again, even here, what we did was we assumed that all the advice was given up front. Okay? It worked great, but the problem was in some of the data sets that we tried when we did the human experiments, it was very clear that the humans like to say things that are obvious. Okay? The humans like to say things that can be inferred from data actually. So what we wanted to do was figure out if somehow we can capture the uncertainty of the model. Can somehow the model itself figure out what it knows, figure out where the mistakes are, and ask a question about that to the user. So that's why it's kind of similar to active learning. That's why we call it as actively seeking advice. As a motivating example, so an advice, let's say in a support vector machine or even a neural network, if I'm looking at a linear case, it's really a polygon. Okay? It's basically giving you a polygon, and an advice is saying inside this polygon the label is black and the label here is blue. Okay? Now the problem is I can give you several types of advice because many of these polygons are still correct. The question is which of this advice is most useful to the model. Clearly giving this and this is not that useful, but maybe this and this or this and this are very useful. Okay? And the system, if allowed to ask questions, could potentially ask in those regions of advice, and that's what we are going for. So we are heavily inspired by active learning. So you can look at the active learning setting. Well, you have an initial model, you generate predictions, you somehow calculate uncertainty of your predictions using say entropy, and you select the examples that have the maximum entropy, right? And so what we are doing is very simple. We have made small changes. We replace the model with a relational model. Instead of selecting examples, you give a knowledge, you give a clause, okay? You give a rule and ask uncertainty over that rule. Okay? So for example, what would a rule look like? Now I'm interested in, let's say, in this problem of predicting which of these states vote Democrat. So this example was before the election. Okay? Now all these predictions go out the window, but that's a different point. Now question is to predict which of these states vote Democrat, and let's say I'm looking at my model now suddenly sees that these are the states that are very hard to predict. They are the swing states. Now the question is, how can I use these swing states and ask a question to the user, right? So what we do is actually we learn clauses. One simple clause says that how about the states on the west side that are ruled by a democratic governor, or how about the states whose primary industry is manufacturing. Okay? So the first query are the green states, these are the orange states, and then the person could say, in this case it's most likely a Democrat, in this case it's most likely a Republican. Okay? Again, I'm using this as a toy example, so it's only binary classes, and that's where it's like active learning, but you can think of again as preferences. Okay? So how do you query these? We query using constructing these trees, and we basically look at examples that have the uncertainty and fit the trees to reflect the uncertainty, take the path from root to leaf, that becomes a class, give that to the user. The class that has the maximum uncertainty, give this thing. We did this again with inverse reinforcement learning. Our best application was flying a drone through a classroom without crashing on any of the walls or the chairs. Works great. We have done this for planning recently, hierarchical planning. I'm skipping for the time. And again, we've got some great results. I'm going to skip all this to wrap up. We've been really trying to do these on health informatics tasks or precision health tasks, looking at cardiovascular procedures, electronic health records. Recently, the one that pumped me the most was predicting postpartum depression from data. So we asked, turns out that with 30 questions on a population of about 120 women, pretty diverse population, we can get 95% accuracy by running our precision recall model on learning from predicting postpartum depression. Again, a whole bunch of other problems. So AI in the wild is more than a single table. We have much data that we have to look at, multiple types of data. These are all central to learning with human, for human aware AI. And sequential decision models, dynamic models are all important. And to deploy, really, we want to do a bunch of different types of problems. But the one that I'm really pumped up about recently is doing machine reading for machine learning. So can I create like a genome of machine learning papers that a new graduate student walks in and asks, okay, I'm interested in this particular problem. Now most of you are deep learning, so I'm going to ignore that, and I'm saying I'm interested in applying active learning with EM. What is the latest work? Or what is the set of papers that I should read? And we should come up with something that is much more meaningful than a simple Google search. So it's kind of like doing the visual genome, but doing that from a machine learning perspective. So I think there's NLP there. There's all domain. Thankfully, we don't need domain experts. We have domain experts, and we can do this. So again, a lot of these future problems that I'm interested in, and a dream problem would be scaling this up. Okay, so I'm done. Thank you. He's been doing this for like 2 minutes. That's what I do to my son. So yeah.
3 minutes for who's count.
All right. Okay.
Any questions for Professor Natarajan?
Yeah.
Yeah, so we are all kind of these days mesmerized by deep learning.
Right.
So what does your work bring to that world?
Yeah, so that's a tough answer. So no, I haven't really explored deep learning as much. So we are more interested in, I guess, human in the loop learning. If I find a way where I can replace my boosting with deep learning and it works equally well, the questions still persist on how can I present the data to the user, get that input back, how can I trade off the precision recall. So figuring that out in the deep learning is still an open problem. Of course, I can make my things much more explainable because they are easy to see. Like I can just construct these classes which are much more easier to parse than a deep learning thing. So you guys are working on explainable AI with deep learning. You have to tell me how to do this. So I don't know how to do this in deep learning yet. But yeah, that.
Yeah, we are trying to figure out, but I think your kind of idea gives us a better handle on how to communicate with people.
Right.
Absent, you know, deep learning.
Right, so that's the thing. So for deep learning, I don't really know how to make it presentable to the user. So I know you guys are working on it. But yeah, figuring that out is still an open problem for me. But the power of logic and relations kind of give me a structure that I can talk at an abstract level, not in terms of instance level, not in terms of values level. That makes the interaction much more easier for me to do. Yeah. I thought there was another question. Yeah.
I'm actually curious about how the performance of your courses depends on the quality of your advice.
Oh, that's a great question. So, yeah, so how much does it depend on the quality of advice? As you see, it explicitly trades off between data and advice. So if you have bad advice but good data at that point, it's still okay. If you have good advice and bad data, that's okay. But if you have both of them bad, then in that region, obviously we are not going to do better. So because we explicitly trade off between data and advice, as long as you have some data with bad advice, that's okay. But what we are now trying to do is also figure out, if I can figure out what your expertise is in, right? So a neuroradiologist might give me good feedback about Alzheimer's images. A normal radiologist might give me good feedback about CT scans, right? So for MRIs, I know whom to ask. For CT scans, I know whom to ask. So if I can somehow figure out the expertise of the person, so it's like the probability of the advice being correct, given that this is the sub feature set that I'm in, the region that I'm in my feature set, then I can have a good question. So estimating, in some sense, I'm kind of going beyond what you're asking, and I'm saying that estimating the expertise of the expert in different areas of this problem space is something that we are just started doing. So that's, yeah, certainly an interesting question. It's an open direction. What if the expert is completely wrong about everything? Then we can do well at this point. Yes. Any? Yeah.
Your experience, how hard is it for people to give advice?
How hard it is for people to give advice? It's actually, again, a great question. It's really hard if you just ask them in the original way. I have this problem. Tell me what you know, right? Then the advice can be very useless and abstract and nonsensical. But the moment you start presenting this way, it's actually easier because we have a hard-coded in-house logic to English translator, and we just, if this is a class, I'm saying hard-coded because we are not learning it. We know if this is the class, this is the sentence, and you convert it into an English statement and give advice, and they are able to give advice. But sometimes it's not easy. Like what if the white matter intensity is greater than 3.5 by the parahippocampus? Who knows what, right? So there you have to discretize it. You can't say 3.5. What if it is significantly high? And then they say, ooh, then that brain is soggy, and you don't need that. So yeah, figuring out how to go from there to here is also interesting. But it's easier if we present some question and get an answer rather than asking for abstract advice.
So what I'd like to suggest is that we'll thank our speaker, and if you have any further questions, feel free to come by and ask Sriraam. Thank you.
Thank you.